talk about titles here. Dino was actually a joint student of Transseries and myself. So just to introduce him, so just also from Croatia, but a few times.
Okay, thank you, Maya, for the introduction. So firstly, I want to thank the organizers, to Maya and Jean-Philippe, for letting me participate to this mini workshop, and I want to thank the general organizers of the program. Okay, so let me just mention that the research done for my PhD is fully supported by the Croatian Science Foundation and this other grant. Okay, and so as Maya said, I recently done my PhD under the supervision of Maya Resman and Tamara Servin. And if you are interested, this is a link to my PhD thesis. And the content of the PhD coincides with these 4 articles. So today I will speak about the content of this first article about the linearization of complex hyperbolic Dulac germs. In my PhD, we also consider the normal forms of hyperbolic logarithmic transseries. I will mention this paper, and we found the normal forms of parabolic logarithmic transseries, and we study normalizations of strongly hyperbolic transseries and strongly hyperbolic complex Dulac germs. So basically, we studied the hyperbolic here and strongly hyperbolic Dulac germs. If you are interested in parabolic Dulac germs, standard Dulac germs, you can consider paper of Mardashic, Resman, Rolan, and Županović, and in 2019. Okay, so let me start. So first, I'll introduce the notion of Dulac germs, and I will describe what is linearization problem in general. Then I will define differential algebra of logarithmic transseries. And first, I will present the linearization theorem for logarithmic transseries. Then the linearization theorem for analytic germs on some domains, which we call admissible domains. They're basically some kind of invariant domains. And then I will combine these 2 results to describe the linearization theorem for Dulac germs and the complex Dulac germs. So let us briefly recall. So what are Dulac germs? They are analytic germs on interval such that they expand in power logarithmic scale. So they have this kind of expansion. These PIs are real polynomials. And this sequence is strictly increasing, tending to plus infinity. Okay. So we have another property of Dulac germs. They can be extended to a sufficiently large complex domains called the standard quadratic domains. We all know this story about the Dulac problem and about this extension. And this extension allows us to have quasi-analyticity property. So it basically means that every Dulac germ is uniquely determined by its Dulac series. Okay, so what are the complex Dulac germs? So Maya today spoke about it. So complex Dulac germs are germs defined on the standard quadratic domain, with this kind of asymptotic expansion uniformly on the domain. With PI, where PIs are polynomials with complex coefficients, and this lambda is complex. Okay, and these exponents are real. Okay, this is expansion in standard Z chart. Of course, we can switch to the, in some point we will switch to the logarithmic chart because our proofs are much easier in the logarithmic chart. Okay, so we call this kind of expansion a Dulac series. If they are complex coefficients, we call it a complex Dulac series. Okay, so what is a linearization problem or finding a solution to the Schroeder's equation? So basically, we want to find some coefficient in C or in R such that this equation has a solution. So F can be Transseries. So here we have, if the F is a Transseries, we have a formal composition. F can be CR map, analytic map, or even Dulac germ or a complex Dulac germ. So what we did, we solved the Schroeder's equation in the class of logarithmic Transseries and the class of complex Dulac germs and also standard Dulac germs, because it is just the special case of this more general theorem for complex Dulac germs. Okay, so we want to examine this kind of equation and we want to solve it. If it is not solvable, then we want to find appropriate normalization instead of linearization. So if you can linearize it, its normal form is basically linear. If not, you want to find the normal form. Okay, so let me go through some basic theorems proved. Some of them are proved recently, some of them are old theorems. We probably all know the famous Koenig's theorem about the solution of Schroeder's equation in the class of analytic diffeomorphisms at zero. So it is proved that using this convergence of the Koenig sequence, we can prove that we can linearize every hyperbolic diffeomorphism at zero. And this Koenig sequence converge towards the linearization. So we can consider two separate problems. One problem is, can we find the linearization? And the other problem is, does this Koenig sequence converge towards the linearization? Okay, so we have some other result. So if you consider the real attracting germ of this form, so we have some bounds, then we can prove that then it can be proved that Koenig sequence converge. Okay, this is probably some kind of improvement. So if F is a real germ which is strictly increasing, and it has a differentiable representative on an open interval such that it's attracting, and we have some boundaries, some bounds for derivation, then it can be proved that the Koenig sequence also converge. There is some result about germs of class Cn. So it can be proved that the Koenig sequence converge for real germs of class Cn. And most recently, there is a result which imposes some logarithmic bounds for a germ. Okay, and for such a germ of class C1, it can be proved that Koenig sequence also converge. And so these are iterated logarithms, and this epsilon should be strictly bigger than 0. So you should have some increase here. So natural question is to be asked, can epsilon be 0? There is a counter example. So here you have 1 plus 0, so epsilon is 0. But if you consider such a germ, the Koenig sequence of f diverge on this interval. So this epsilon is very important, as we will see later, even in the formal case when you consider the Transseries instead of germ. Okay, so there are two questions. First question is, can we solve Schroeder's equation in the class of logarithmic Transseries? And the second question is, can we solve Schroeder's equation in the class of complex Dulac germs? Okay, so what are our tools for solving these, for giving an answer to these questions? So for the case when we consider the linearization of logarithmic Transseries, our basic tools are fixed point theorems. And for solving this problem, the basic tool is convergence of the Koenig's sequence. Okay, so today I will not spend much time talking about this formal linearization because this talk can be considered as a sequel to talk given on geometry and model theory seminar last week. So I will briefly just mention this formal linearization, and then I will skip to this for today more important problem. Okay. So the first part of the talk, we want to solve the Schroeder's equation in the class of logarithmic Transseries. So let me just define what is logarithmic Transseries in our setting. So we work with a formal variable at 0, z, and this is a formal logarithm, and inductively we define Ln. So what is Lk infinity is the set of all formal sums of this type. So these coefficients are real, and here you only have logarithms of the bound depth. So your depth is bounded with k through all monomials of this formal sum. Okay, and our support is well ordered with respect to lexicographic order. Okay, and we can use this notation. We call it a blockwise notation. So we can consider this type of Transseries as a usual power series, but with the coefficients, with the block coefficients. So what is a block? It's just a Transseries in else. Okay. And this set of exponent is also well ordered. Let me introduce some notation. So this is a notation for a coefficient. Okay. Order of f is a minimum of the support. And if order of f is positive, then we call f the logarithmic Transseries of depth k. Okay, so Lk is a space of all logarithmic Transseries of depth k. Of course, we can define the order in Z. What is ordered in Z? Since this set of exponents is well ordered, we can take the minimum of these exponents of powers. So it's ordered in Z. And we have the usual derivation monomial by monomial, which makes our set Lk a differential algebra of logarithmic Transseries of depth k. So we define a tower of logarithmic Transseries, and when we take a union, we get the differential algebra of all logarithmic Transseries. So what is important here, that when you take the element, some Transseries inside, the depth of logarithm is bounded by k. Okay, so what about the composition of logarithmic Transseries? So, of course, main goal for the definition of composition is that LK should be closed for the composition. Of course, it is easy to see that we cannot define the composition in such a way that LK is closed. Because, for example, if you compose L1 with L1, you get L2. This is in L1, but this is in L2. So you cannot stay inside the same class. So we have to make some restriction on our space. So we consider the set of all logarithmic transseries without the logarithms in their first terms. Okay, and this alpha is strictly bigger than 0 and lambda is strictly bigger than 0. So we distinguish, as in usual theory of power series, we distinguish 3 types of such transseries: parabolic one, hyperbolic, and strongly hyperbolic. Since we are considering the linearization problem, we will deal with hyperbolic transseries. Okay, so how to compose in this class? So you take any f, which is an element of LK. So we have to make some restriction with this transseries, but not with this. We can take arbitrary element of LK, and on the second place, so we composed with the element of LKH, and this is the usual Taylor expansion. It can be proved that this family is summable, so this is well defined. Okay. So there is a notion of composition, and we can try to solve the linearization equation, Schroeder's equation, in the class of hyperbolic logarithmic transseries. So I just forgot to mention that so we want to solve this equation, and this solution should be parabolic logarithmic transseries. Okay. So we have our main theorem, linearization theorem. So if you start with hyperbolic logarithmic transseries f, this HOT means higher order terms, and your lambda is between 0 and 1, we can write our f like this. So this is a initial part of our transseries f. Okay, this is a linear part, and this is just f0. So you take all monomials of order between 0 and 1, 1, 1, 1, 1, 1, and so on. And we can prove that this is our normal form. Okay, so there is the first statement. So there exists a unique parabolic logarithmic transseries such that it's a solution of this equation. So what is important here? It's important that in F0 here, we cannot kill any term, and we cannot change these coefficients. So it's minimal normal form. Okay, so when can we linearize our hyperbolic transseries? Only if this, only if we can kill, only if there is only if every alpha, every AM is equal to 0 here in F0. So if and only if F0 is linear. So maybe we can write it like this. We can linearize our hyperbolic transseries if and only if the order of f minus lambda z is strictly bigger than 1, 1, 1, 1, 1. So if and only if we don't have this part. We have only this, and we can kill every term inside. Okay, so we have necessary and the sufficient condition on transseries in order to be linearized. Okay, So there is the last statement, which gives us a nice algorithm how to deduce what is how to find normalization. So basically, if you take any initial condition such that first block of order 1 coincides with the first initial block of normalization, then you have a convergence of this. We call it a generalized Koenig sequence, because in the standard Koenig's case, this is just this is linear. This is just multiplication with this. So we can prove that this converges towards the normalization. Okay, and this convergence is done in, we call it a weak topology. So what is a weak topology? It's very nice topology because you just consider the coefficients attached to some order, and you prove the coefficients converge. Okay, so we have a nice algorithm how to find normalization. Okay, and if F0 is linear, then we are speaking about the linearization. Okay, so let me just go through some examples. So for any lambda, strictly bigger than 0 and unequal to 1, we can prove that every hyperbolic power series can be linearized. So in L0, every element can be linearized. If we move to L1, so consider this Transseries in L1. So the order of this monomial is 1, 1. So this should stay inside F0. But everything here is strictly bigger than 1, 1, so we can kill every term here. So this is our normal form. The second example, also in L1, shows us that this Transseries can be linearized. Why? Because there is nothing in between 1, 0 and 1, 2. Okay, and we can kill this and all the rest, and we can linearize Transseries. Okay. So before going further, so it is interesting that in L2 there are two types of normal forms. First normal form is linear, and second normal form is not linear. It's of this type with some a not equal to 0. Okay, so they are both finite. And if you move to L2, we'll see later, your normal form, your F0 can be potentially infinite. Okay, so we have one important result, is that every hyperbolic Dulac series can be linearized, and the unique linearization is again Dulac series. So one can see easily that every hyperbolic Dulac series can be linearized. Why? If we go back, so this is Dulac series, and this alpha I is strictly bigger than alpha. So in case when you are considering the hyperbolic one, then this alpha is 1, and alpha I is strictly bigger than 1. So your F0 is linear. So it's an easy application of the linearization theorem to prove this fact. And something that is not so easy is to prove that this linearization is again a Dulac series. Okay. And we have another example. So this example is in L2. So here you have 1, 1, 1. So this should stay inside F0. Okay. And here you have 1, 1, 2. So you can kill this, this. You can kill the rest. And the example when you have infinite F0, when you have infinite normal form, is following. So you consider the Transseries in L4. So here the exponent of L1 is 0. So this should all stay inside F0. The exponent of L2 is 0. So this stays inside. And now you have 1, 2, which is strictly bigger than 1, 1, 1, 1. And you can kill this term and all these terms. So this is your normal form, which is infinite. So it can be proven that, so if you are in L0, you can linearize everything. If you are in L1, there are two types. If you are in L2, there are infinite in many types, because your normal form can be infinite. Okay. So, okay, that is all about this formal result. So, our main goal is to prove that every complex hyperbolic Dulac germ can be linearized. So, if you take any hyperbolic Dulac germ F and its hyperbolic Dulac series, they are connected by asymptotic expansion. So we can obtain a formal linearization by the previous theorem. Okay. And we want to prove now that there is an analytic linearization. And the last question is a formal linearization, which is a parabolic Dulac series, is this asymptotic expansion of analytic linearization? So we want to solve two questions. First, we want to find the linearization, and then we want to check if this formal linearization is its asymptotic expansion. Okay, so we generalize this problem. We could approach it like this. Okay, we can prove that every hyperbolic Dulac series can be linearized. It's enough, but we generalize it and we prove the stronger result. We found necessary and sufficient conditions for every hyperbolic logarithmic transseries to be linearized. Okay, same is here. So instead of considering only hyperbolic Dulac germs or hyperbolic complex Dulac germs, we will generalize it and we will consider arbitrary analytic germs on invariant complex domains called admissible domains. So why to do it like this? Because in order to prove that the Koenig sequence of hyperbolic germ converge, it is sufficient to have first two terms in your asymptotic expansion. There is no need for considering all terms in asymptotic expansion, just first two terms. So we generalized this result, and we prove that any analytic germ on some special domains, complex domains of some hyperbolic logarithmic bounds can be linearized. And then we apply this more general result on hyperbolic complex Dulac germs. Okay. So we proved this, okay, on the formal setting. Then we solve the Schroeder's equation in this more general setting, and then we apply both to connect this analytic linearization and formal linearization. Okay. So about the first problem. Suppose that map F is defined on some domain, which is a subset of C+, and it has the following asymptotic bound of this type. So all this is done in a logarithmic chart. So in logarithmic chart, lambda z, which is linear, becomes a translation by this beta should be minus logarithm lambda, and this beta is element of C+. So it has positive real part that is important. Okay, so instead of z going to 0 in standard chart, we have a real part of zeta going to plus infinity. Okay, and we have this kind of bound. So there is a question: can we find some sufficient conditions on our starting domain such that there exists R, such that if we move further to further on the right, that this new domain dr is F invariant. Okay, why we need F invariant domain? Because we want to prove the convergence of the Koenig sequence. Okay, and in order to prove the convergence, to make sense of the Koenig sequence, you have to have a F invariant domain. So what is our solution? We will define the notion of admissible domains, and we will use admissible domains to be sure that we can produce an F invariant subdomains. And then we take Koenig sequence on such smaller domains. So that is the idea. So the definition of admissible domains looks more complicated than it is actually. So I don't have much time, but I'll try to explain it very briefly. So you take any beta in C+, any epsilon strictly bigger than 0, and any k. Why? Because you have this type of bound here. Okay, and epsilon is strictly bigger than 0. And then you define m, and you defined this, okay, as a real part of beta plus minus this m. Okay, so how to define the admissible domains? We first define two functions, HL and HU, whose graphs bound the domain from below and from above. Okay, let me go through some picture. So this is a graph of HU, and this is graph of HD, and we want to consider such domains with the imaginary part of zeta between graphs. Okay, but there are some properties that HU and HD should satisfy. Sorry, this is HL, not HD. It's a mistake. Okay, so first property, of course, is that HL of X is strictly smaller than HU. So it's obvious condition. And let me just talk about this condition, okay, for HU. HU is an increasing map with this property. So let me explain this property. So basically, since you have some bounds on our F, so our F is a translation by beta. It's translation, it's basically zeta plus some beta plus something that is very, very small. And so F of zeta should stay inside this square. And this is delta minus. Sorry, this is delta minus. Okay. And if you take zeta plus beta, here, this is m. So it's plus minus m. So that is why this kind of condition. As you move forward, even if you start from this point, your square should stay inside. And this is a coordinate of x coordinate of this point. So we have it here. Okay. So the same is for HL. If HL is increasing map, here HL is increasing and should satisfy the similar condition. And the other condition, of course, if HL is decreasing, since we have a translation by beta and the imaginary part of beta is strictly bigger than 0, then HL obviously satisfied our condition that this square should stay inside our domain. Of course, in between these two graphs. Okay, so I only explained the case when imaginary part of beta is strictly bigger than 0. There are two more cases when beta is strictly real and when imaginary part of beta is strictly less than 0. Then you have this kind of translation. Okay, so we have a following notion: DHL DHU is just this. Okay, so it's space in between graphs. So what is, when we fix these coefficients, what is the domain of this type? It's just an arbitrary union of such domains. And what is admissible domain is a domain that contains the domain of this type. So this is domain of type beta epsilon k, and this is admissible domain. Why? Because it contains at least one such a domain. Okay. So there are some there are some examples of upper maps and lower maps. So we call this HU an upper map and HD a lower map. So there is a criterion for upper maps. So if you start with an increasing map of class C1, such that its derivation tends to plus infinity. So it looks like this. So your derivation tends to plus infinity. So you can cut. So this is T. You can cut your domain, and then the remainder of this graph will be a graph of an upper map of this type. Okay. And we can apply this result on such class of maps with R bigger or equal to 1. These kind of maps are examples of upper maps. And what is very important for us here, since we are working with complex Dulac germs, it can be proven that every standard quadratic domain, if you start with some standard quadratic domain and you fix some beta, epsilon, and k, what you can do, so this is a standard quadratic domain, you can find R such that this is an upper map and this is a lower map. So basically this is a domain of type beta epsilon k, and since our standard quadratic domain contains this domain, it's admissible. So it is very important that every standard quadratic domain is admissible domain. So this standard quadratic domain will produce invariant domains. So we should be able to take Koenig's sequence and to consider the uniform limit of the Koenig sequence. So this proposition tells us that if we start with some domain which is admissible of this type, and we have a germ on such a domain with this kind of bounds, these L1 to Lk are just iterations of the logarithm. Then we can prove that there is R big enough such that if we move forward enough, then we get F invariant subdomain. Okay, so what is this DFR? It's just DF is a maximal F invariant subdomain, and R means that you just moved forward, moved to the right enough in order to produce something which is invariant. Okay, so basically this proposition tells us if you start with the admissible domain of this type, you should be able to find a F invariant subdomain. Okay. And now we have the linearization theorem for such a maps. So if you start with a map with this kind of bounds and on admissible domain of the same type here, then you can prove there is a analytic linearizing map phi such that it's a solution of a linearization equation. Of course, it's just a translation, but this is in a logarithmic chart. So linearization is just switching to translation. Okay, and moreover, this linearization can be obtained as a uniform limit of the Koenig sequence. So now in the logarithmic chart, the Koenig sequence looks like this. Okay, so what is important for the standard Dulac germs? Standard Dulac germs preserves the real line, not the complex one, but the standard Dulac germs. So what is important here is if original F preserves the real line, then also the linearization preserves the real line. Okay, that will be important later. And of course, we can prove that our linearization is unique. So if you take another linearization, which is parabolic, then it coincides with the limit of the Koenig sequence. Okay. So let me just emphasize this. So this epsilon here is strictly bigger than 0. And this is this L1 is a logarithm and Lk just k iteration of the logarithm. So if we go back to this result, so it's basically similar result. This is done for real C1 germs. Okay, and it is done in standard chart. Okay, so this epsilon is important in our linearizing theorem for analytic germs, and it's important in the formal case. So let me go to the formal case. Here we have 1, 1, 1, 1. So if you take a germ with order 1, 1, and 1 plus something, then you can kill it. Okay, but not you cannot kill this term. So this epsilon is also important even in the formal case. Okay. I have maybe 10 minutes more. Okay. So this is our result for analytic germs with some kind of hyperbolic logarithmic asymptotic bounds. And the only thing that is important is that we have first two terms, not the whole asymptotic expansion. And we come to our main theorem for today's talk. It's a linearization of hyperbolic complex Dulac germ. So if you start with any hyperbolic complex Dulac germ, of course, in the logarithmic chart on a standard quadratic domain, there exists a unique parabolic germ, which is a solution of this equation. So we already proved it because we have this theorem. And for Dulac germ, you have even better bounds. Okay, so we can apply this theorem. And our standard quadratic domain is an example of an admissible domain, so we can apply this theorem. So it's basically application of this theorem to prove that there is analytic linearization, which is not so trivial, is to prove that our linearization is complex parabolic Dulac germ. Okay, it's easy to prove that it's parabolic, but it's not so easy to prove that it's a Dulac germ again. So the obvious candidate for its asymptotic expansion is just the formal linearization. Since we proved that formal linearization is again Dulac series or complex Dulac series. So let me go briefly through the sketch of the proof. So first step in the proof is, of course, working in a logarithmic chart. So in the standard Z chart, you have this type of linearization equation. If you switch to logarithmic chart, this is plus beta, so you get some translation. Okay, and if you start with Dulac series of this type in Z chart, in standard chart, switching to logarithmic chart, you get this type of expansion. Okay. So the second step is to consider we call it the homological equation on the standard quadratic domain. So let me go from the end to explain why we consider this type of equation. Of course, you can rewrite the linearization equation in this way. So it's basically, you can write it like this. Okay, so we just consider this part, and instead of b, we take arbitrary h with these bounds. Okay, so what we want to prove, we want, if you take phi hat, which is a formal linearization, and you take analytic linearization, you can rewrite phi hat as formal sum of partial sums. Okay, and you want to prove that this has this type of bounds, exp of minus beta and zeta. Okay, so you want to prove this, because it basically proves that this phi hat is a asymptotic expansion of phi, and we are done. So how to prove this? So you put this inside the linearization equation. So instead of phi, you put phi minus phi n. Okay, and it can be proved that you get this type of bounds. And then you try to solve this type of equation generally. Okay, you take such bounds here, arbitrary h, and you try to solve it. And we use the idea from book of Frank Lore. He did the similar idea for when he considered the construction of the phi2 coordinate. So you just prove that this is a solution of such an equation, and then using this, you can prove that if you started with these bounds, okay, then your solution have the same bound. So if you start with this bound, your solution is unique and have the same bound. But since this is a solution of such an equation, it should have the same bound. So basically, that's the proof that phi hat is asymptotic expansion of phi. So that's it about today's talk. This is just bibliography that I used in my papers and PhD. And of course, thank you for your attention.
Thank you, Dino. Thank you, Dino. Questions or comments? Well, I may have questions. So, in order to summarize what is known about this question of normalization of Dulac germs, so you explain us today what we know in the case of hyperbolic Dulac germs. What about, so what is the state of the art for parabolic Dulac germs?
For the parabolic Dulac germs, the situation is very much complicated. Let me just, so this for parabolic Dulac germs is done in this paper. So with the parabolic, as we know in this story for a usual power series, there is of course problem with avoiding the residual term. So if you start with some parabolic series, for example in L1, Z plus ZL1 plus something, then your normal form is, so I will write here C, it's just Z plus Z squared L1 plus the residual term. Residual term is 2 times 2 minus 1, it's 3, and then 1 times 2 plus 1. And then we have some C, and we have a formula how to calculate C. And our normal form is finite, but if you have something in the first block, if you start with Z plus Z1 plus some else here, then your normal form looks like this, but here you may have infinite number of terms that you cannot kill. So, and this whole procedure involves a lot of technical details, a lot of dealing with formal differential equation on the spaces of blocks, and using some fixed point theorem. One is especially important. It is motivated by the Krasnoselski fixed point theorem, but it's a long story.
So you're saying that even for Dulac parabolic series, the situation is complicated.
Yeah. Yes.
And do you know anything about germs? I mean, Dulac parabolic germs. Is there something known, or what is the situation?
There is a paper about what I just mentioned about the standard Dulac germs, parabolic germs, but I didn't investigate it further. I just considered the strongly hyperbolic and hyperbolic Dulac germs for the analytic case.
So for, my last question is precisely that one. What about strongly hyperbolic germs? Dulac germs.
About strongly hyperbolic. So for strongly hyperbolic, on the formal part, any strongly hyperbolic Transseries can plus something.
Could you, Dino, sorry, could you recall what strongly hyperbolic means.
Aha, okay.
Not everybody is familiar with the terminology.
Yeah. Of course. Okay, here. So if you start with Transseries without the logarithmic Transseries without the logarithm in its first term, so we'll say that it's strongly hyperbolic if this lambda is strictly bigger than 0, alpha is strictly bigger than 0, and it's not equal to 1. It's somehow strongly repelling or strongly attractive. And it can be proved in my fourth paper that all such Transseries can be conjugated via parabolic conjugation to their first terms. Okay, so normal form is very simple.
Okay, so strongly means that the expansions start with a power which is not 1.
Yeah. And we have this nice result that any can be conjugated to its first term. Okay, and so when you consider the Dulac germ or complex Dulac germ, then it can be proved that any strongly hyperbolic complex Dulac germ can be analytically conjugated to this type of germ, of course via parabolic Dulac germ or parabolic complex Dulac germ.
So this is via a version of Butcher's sequence or this kind of thing?
Yeah. Instead of considering the Koenig sequence, so instead of so Koenig sequence is just considering this, okay, in the hyperbolic case, and some version for strongly hyperbolic case we call it a Butcher's sequence. So this is Z composed with F. So we just take the inverse of this. Okay, and of course, in the strongly hyperbolic case, you can kill this.
Sure.
Yeah. So basically, you have this type of Transseries, and you can consider this type of series, and you prove that this converge towards the normalization. So
again, you use your technology of admissible domains, this kind of thing.
Yes. But the terminology is the same, but the definitions are very different because we have to adapt it to other type of problem. It's
okay. Are there any other questions? So here.
Okay, nice talk. Thank you. So for maybe for hyperbolic, almost everything is after what you said, almost everything is okay. What about when you consider parabolic Dulac germs, but that came from planar vector fields? I mean, just, and if you impose, have you know if it something is nominal, but if you impose conditions for this planar vector field, I mean, for instance, having a integrating factor or something like that, this can help to do something, or
I really don't know. I didn't think about it at all. I don't know at the moment.
I was thinking of the first of result proved by Musu and Roche, then put it the condition that at every corner in a polycycle you have an integrating factor. Yes, it was an analytic. Yeah, so maybe I don't know for this kind of problem, it could be something to study. I don't know.
I mean, the thing that I really follow, so it was a parabolic germs, parabolic large germs, but we allowed ramified, like Dino does, changes to variables. So we want to conjugate them to normal forms by more or less power log Transseries. And so I think that so if you try to do it, it's completely different than in case of making equivalence of a saddle, where you have your corner Dulac map by regular, by analytic changes. And the normal form that we usually have for Poincaré Dulac normal form that we get by conjugating the saddle by regular, by analytic changes of variables, will not correspond to our normal forms. So what I'm saying is that even if it is, even if you take a corner mass that is integrable, that is in a Poincaré Dulac normal form, you will have non-trivial analytic class with respect to ramified power logarithmic conjugacy. So it's a different problem, and I think it's not, it wouldn't help much.
Okay, so no other questions in the room or online. So thank you very much, Dino. Let's thank Dino again.
Thank you.